Hi everyone, so today we will continue with the chapter 9. We started with estimation. Let me refresh your mind briefly. So the basic concept was that we have a population. The population looks something like this. The mean of population is somewhere mu. If we know the mean of the population, then we know that, based on the size of the sample that we are taking, that our sample is with a 95% probability within this range. Now, how did we calculate this range? We looked up in the table when we calculate the z-score, and what we did is we cut off the 2.5% most extreme values to the right and the 2.5% most extreme values to the left. So essentially, the very high values that are very improbable to have and the very low values that are improbable to have, you cut them off. If we take out 2.5% on each side, accordingly what is left in the middle is 95%. That's our 95% confidence interval. So accordingly, if you would cut off, for example, 5% on each end, let's say here and here, we would cut off 5% instead of 2.5%. What is left in the middle is would be the 90% confidence interval, and so on and so forth. So we can also create a 98% confidence interval or a 99% confidence interval. Those are usually the most common ones. But you can also create a 99.5% confidence interval, for example. So let's stick with the 95% confidence interval, as I mentioned. So we cut off 2.5% tail in the left, and we cut off the 2.5% tail to the right. The values, if you remember, so for cutting off the 2.5% tail to the left, we need to look for the value z-score of 2.5%, and that would be here, 1.96, right? 1.9 and 6 is the second digit after the decimal, is exactly 2.5%. So it means we are here minus 1.96 standard deviations to the left, and if we look it up for the right tail, it would be essentially plus 1.96 standard deviations to the right. And very similar is if you would want to do it for a 90% confidence interval, you would cut off a 5% tail, and the 5% tail would be exactly here, exactly between these two values, right? This is 0.0505 and 0.0495. So exactly between these two values, so between minus 1.64 and minus 1.65, it should be minus 1.645. Again, for the 90% confidence interval, we would cut off minus 1.645 standard deviations to the left and plus 1.645 standard deviations to the right. Right? So which means the interval width is lower, is less, so which is nicer because we come up with a narrower interval. But of course, the probability that we are wrong is higher. The chances that we are wrong would be 10% instead of 5%. Now, what we do is that we know if the mean has the value mu, and we know the standard deviation, we can get it from the sample. Standard deviation gives us an estimate of the standard deviation of the population. So we know then that with 95% probability we are within this interval. Now, the problem is when we want to do estimation, we do not know where this value of mu is. We have no idea where this is. Until now, we always knew where this is, but when we want to estimate, mu is exactly what we want to figure out. So what we do is we have to turn around everything, and this is a little bit the trick that we use. So it's a little bit tricky. We take a sample, and the sample gives us some value. Our sample mean could be whatever, x bar, let's say it's here. We observe this value. Now we don't know, is this value that we observed here or here, is it to the left or is it to the right of the mean? How close or how far is it from the mean? So what we do is we turn around the trick and we say, if we take a sample here, then let's calculate that the mean with 95% probability would be within what interval. So if we would essentially go 1.96 standard deviations to the right of our sample and 1.96 standard deviations to the left of our sample. Let's say here, minus 1.96. And then we know that the mean of the population with 95% probability must be in this interval, right? So again, we do not know where this mu is. We take a sample and we do an observation of our sample mean. All we have is the sample mean. We have also the sample size, obviously. We know what is the size of the sample that we took. And we have the standard deviation of the sample as well, that we can observe as well and calculate. And based on the sample mean that we are calculating, we can build an interval around that sample mean where we know that the true mean of the population must be in this interval with a 95% probability if you have chosen a 95% confidence interval. Of course, if you would choose a 90% confidence interval, that interval would be somewhat smaller, which is nice, but then the chances of being wrong would be higher. So this is essentially the basic idea of what we do here when it comes to estimation. Okay, here is an example. We asked adults over 50 who watch regularly network news cases to see if they contacted the physicians to ask about some prescription drugs that were advertised on the newscast. To be more concrete, we asked 693 adults, and out of those 693 adults, 104 said that they would contact their physician regarding a prescription drug. So we want to come up with an confidence interval. To be more accurate, is asking for a 95% confidence interval. We're supposed to produce it to see what percentage of adults would ask their physicians regarding the prescription drug that is advertised on TV. The way we do it is that formula that we use. So again, what we have is here our sample mean, which is in this case the percentage of success, which is 104 out of 693. Plus or minus, and then we have to calculate the standard deviations, and in the binomial case, we know that the standard deviation, the formula for it is this one, right? So the probability that we calculated in our sample, which is 104 out of 693 times 1 minus p divided by n sample size, which is 693, and square root of that. And then this z is the z-score of the confidence interval that we want to calculate. If you remember, hopefully alpha was the probability that we are wrong. So for a 95% confidence interval, alpha is 5%. It's the probability that we are wrong. So essentially, alpha half is 2.5%. So plus or minus 2.5%. This is exactly reflecting the fact that we are cutting off the two tails, the two most extreme tails, the 2.5% to the left and the 2.5% to the right. So my sample mean times the number of standard deviations where I have to cut off. So for a 95% confidence interval, it would be 1.96 standard deviations to the right and to the left of that mean. And then how large is the standard deviation itself, right? So let's take a look. All we need to do is to plug in the numbers. What is the p hat? So the success probability in our sample, it was 104 out of the 693 people that we asked. If you do the math, you should get exactly 15%. So p hat is equals 15%. And the z-score that is appropriate to our confidence interval of 95%. I just talked about it a couple of times. You need to look it up in the table. And it is 1.96. So plus or minus 1.96 standard deviations to the right and to the left of what we had. So essentially, this 15% is kind of like our sample mean that we got, right? So the probability of success was 15%, plus or minus 1.96 standard deviations. Now, what is the standard deviation? It's essentially this formula p hat times 1 minus p hat. So 15% times 1 minus 15% divided by n, which is 692. If you do the math, this value, square root, multiplied with 1.96 is 0.026. So 15% plus or minus 2.6% essentially. And if you do the math, you get a lower confidence level of 12.4% and the upper confidence level of 17.6%. Right? So between 12.4 and 17.6% of the people are asking their physician regarding a prescription drug. And that is with a 95% confidence interval, right? So we got here a value of 15%. And then if we add the 1.96 standard deviations, what we get is here 17.6%. If we subtract the 1.96 standard deviations, what we get here is, 12.4%. Right, so that is my 95% confidence interval. Of course, I might be wrong with a probability of 5%. Right, so that's what it is essentially. This is the basic idea behind it, behind estimation. What we got here is an interval between 12.4 and 17.6%. That's how many of the adults we believe will ask their physicians regarding a prescription drug. And we might be wrong with our estimate with a 5% probability. So depending on why we need that information, that interval between 12.4 and 17.6 might be good enough for us, right? But it might be too wide between 12.4 and 17.6. I need it more accurate, right? So if you need to narrow down this interval width, well, one way to do it is obviously to give up some of the probability of your confidence. So if you are okay with the chance of being wrong with a 10% probability, obviously you don't need 1.96 standard deviations to the left and to the right. What you would need would be simply 1.645 standard deviations to the left and to the right for a 90% confidence interval, right? And that gives you a narrower width of your estimate. You might, however, don't want to go that compromise, right? So you might want to have still the 95% confidence, but a narrower width of your estimation. The only way to do that would be increasing n, increasing the sample size. Increasing the sample size, because it's the denominator, it would yield a smaller value here, so the width of your interval, which is plus or minus this value, the width of your interval would go down. So that's the only way to do it. So that's something to be aware of. So the width of the interval, if it's very wide, it provides little information, right? So for example here, if you come up with something for an election and you come up with an estimate that 95% confidence that of your estimation, that between 9% and 88% of the voters will vote for the candidate A. People will laugh at you if you come up with that estimate, between 9% and 88%. Really, like this is something that it's not really useful if you come with an extremely wide interval. So that's something to be aware of. There's that's not what you see usually on TV. What you see is usually something like that. There's a 95% confidence that the candidate gets between 52 and 56% of the votes. Of course, that's a lot more useful. So as I mentioned, if you look into the width, you want to narrow that width, you have only two ways of narrowing down. A smaller z-score, which comes with a lower confidence level, right? So having 1.645 instead of 1.95, which means we have a 90% instead of 95% confidence interval. The only other way to do it is increasing the sample size. So the n here in the denominator, if the n is larger, then you also get a narrower interval width. And so graphically, again, let's take a look into that. So again, you can have a narrower width of your interval if you choose a narrower confidence level of your interval. So for example, 90% instead of 95%, because now you're cutting off larger tails. You're cutting off a 5% tail on each side for the 90% confidence interval, whereas before you were cutting off a 2.5% tail for the 95% confidence interval. So, in other words, if you increase the sample size, so that's the only other way. If you increase the sample size, you can achieve the following. Either you can just narrow the width of your interval without losing any confidence with the same level of confidence, or you can have the same width of interval with a higher level of confidence, or you can have a combination of the two. So you narrow a little bit the width of your interval of your estimation, and at the same time you increase a little bit of the confidence of your estimation. So all those things is what you can achieve with a higher sample size. Obviously, the disadvantage of the higher sample size is that the cost of obtaining the additional data. You need to ask more people for your survey instead of less people. So obviously, it's always that that compromise that you have to go. I mentioned that a couple of times throughout the semester. So that's it for chapter 9.